Okay, yeah. Our second speaker for today is Frank Trujillo. He's a postdoc at the University of Zürich, and I think you're working in the group of Corina Ulrich, right? Correct me if I'm wrong.
Yeah.
He's also doing dynamics. Even though Frank is in Switzerland, just like myself, we've never met in person. But I'm currently trying to make an effort to get to know more postdocs in my field since I got back here. So I'm very excited to hear about Frank's work. Yeah, the stage is yours.
Thank you for the introduction, and thank you very much for the invitation. I'm very happy to be part of the Quasiworld seminar. I just hope I won't disappoint you much, because actually the quasi-conformal techniques and complex dynamics will be somewhere but a little bit hidden, won't appear explicitly in what I will explain today. But I will try to say exactly where these things appear in the theory. So today I want to talk to you about critical circle maps. So what are critical circle maps? These are just a particular class of circle homeomorphisms. So I will take a smooth circle homeomorphism, and I will say that this homeomorphism is critical if I have a finite set of critical points, which is, I will assume always it's non-empty. And I will suppose that close to this critical point, I can write my map in this form. So basically, up to changing coordinates appropriately, I can think this as some power map, okay? So in general, you can just imagine my critical circle maps is a smooth circle homomorphism with some critical points. And at these critical points, the map behaves like you can think x to the power 3. This is basically what I'm considering. Okay, so this exponent that I have here in this formal definition is sometimes called the power law or the criticality. And it turns out that for a circle homomorphism, not necessarily critical circle maps, if you don't have periodic points, then your map is uniquely ergodic. So today what I want to do is to discuss a little bit of the properties of this unique invariant probability measure associated to critical circle maps. Okay. So since I will be speaking about circle maps, I will need to recall some of the facts of the basics of the theory. So I will start by recalling what's the rotation number and some of these properties that will be used throughout the talk. So the rotation number is some of the most, I guess, is the most important invariant for circle maps. It was introduced by Poincaré, and it tries to measure how much my map is rotating points in average. So basically, I start with some circle homomorphism, and I want to measure how much my map is rotating points. So if I want to give a proper definition to this, how much I'm rotating, I will need to do a little bit of a technical step. I need to go through the lift of this map to give sense of this displacement. And once I go to the lift, so I go to a map, increasing map from R to R, I'm able to define this limit. So this limit, this big F of n, is basically telling me how much my point has moved after n iterations of my map. And then when I divide by n, I'm basically taking the average of this displacement, and I just consider the limit. So this is what we call the rotation number of F, and it turns out that this does not depend in the initial point I consider. It does not depend on the lift. So it's a well-defined quantity, which again is basically the most important invariant in circle maps. Okay. So some of its properties, if I have a circle homomorphism, as I mentioned before, the rotation number is invariant by topological conjugacy. It turns out that this number is rational if and only if my map has periodic points. And if my rotation number is irrational, then my map is semi-conjugated to a rigid rotation. So what do I mean by semi-conjugated? This just means that I have a surjective continuous map, which verifies this equation. So just the definition of semi-conjugacy. And moreover, it turns out that if I can say that at least one of the orbits of my map is dense, then this semi-conjugacy can be somehow upgraded to a conjugacy. So in general, I'm either semi-conjugated or conjugated to a rigid rotation. And one of the most important properties for me in this talk will be If I don't have periodic points, that means if my rotation number is irrational, I have a unique invariant measure. Okay? So these are some of the basic properties. And from now on, I will only consider circle maps without periodic points. So if it's not written somewhere, my rotation number is always irrational, I don't have periodic points, so I have a unique invariant measure. And today I will be discussing properties of this unique invariant measure. Okay? So just a few conventions I will do throughout this talk in case I forget. Every time I say a circle map, I will mean just an orientation preserving circle map, circle homomorphism, sorry. The rotation number will be always denoted by rho of f. And just to make my sentences shorter, when I say irrational circle map, I will mean a circle map without periodic points, with irrational rotation number. And I will denote its unique invariant measure, since I will be only speaking about maps with irrational rotation number, by mu f. Okay, so these are some of the notations I will use during the talk. And now I will go back to critical circle maps. So some of the properties of critical circle maps, I will consider its unique invariant measure mu f. And it turns out that if you add a little bit of regularity to your map, you suppose that it is at least of class C3, then this unique invariant measure is actually singular with respect to the Lebesgue measure. So singular, meaning the usual thing, is just I can find a set that has full measure with respect to my invariant measure, but that has zero Lebesgue measure. Okay? So the moment that we have this, we can ask about the following. How small can this set, this full measure set, get? And if I'm trying to measure how small this set can be, I need a definition, a way to measure how the smallness of this set. So a way of doing this is through the Hausdorff dimension. So for this, I define, and so there's this notion of Hausdorff dimension of a measure, which is basically we consider all the sets that have full measure, and I consider their Hausdorff dimension. And then I take the infimum of all these sets. So I will just take the infimum of the Hausdorff dimension of all the full measure sets. This will be the dimension of my invariant measure. So since I already know that my measure is singular with respect to Lebesgue, now the question is, okay, what can you say about the Hausdorff dimension of this measure? So my objective today is the following. I just want to try to relate the Hausdorff dimension of my invariant measure to the rotation number. So depending on how familiar you are with the theory of circle maps, you may find this relation something to expect or something completely unexpected. But as I was mentioning before, this rotation number is a really big invariant, and it encodes a lot of information. So we shall see this really characterizes to a big extent our map. So at the end, it won't be so surprising to have a dependence only on this rotation number. But my goal today is to really give explicit formula to say how this dimension really relates to the rotation number in a very particular way. So we'll try to give some inequalities relating the Hausdorff dimension to the rotation number. And the only thing is that since I will be speaking about Hausdorff dimension, I feel compelled to define what Hausdorff dimension of a set is, which is not usually an easy task. So I will try my best. I will try to give the formal definition. I really think that most of you have seen this already, so I hope that you won't get very lost. But in case you have not seen it, and in case you get a little bit lost, I will try to make an example afterwards. So at least the example will give some intuition. But I really feel that I need to define what it is. So here it is. I need to define the Hausdorff dimension of a set in order to give sense to the Hausdorff definition of the Hausdorff dimension of a measure. So we start by defining what is called the Hausdorff content. So I have a set. I will consider open covers of this set, and I will consider this nice formula here. So I won't try to read the formula because it gets a little bit technical, but I will try to give an intuition. So as you know, if I have a set, any set, I can approximate its measure, its Lebesgue measure, using open sets. I can always consider open covers of my set. And if I take the infimum of the Lebesgue measure of all the open covers, what I recover is the Lebesgue measure of my set. So basically, if you consider here d equal to 1, so if you consider here d equal to 1, what you recover is just the Lebesgue measure of your set. Okay, but if you have a set that has 0 Lebesgue measure, then you can try to say, okay, what happens if I don't consider d equal to 1, but I will consider d smaller than 1? In this case, these sums here, they are getting bigger. Okay, because I will be considering open covers, which verify this property. My open covers are such that every element of my cover has a small size, has a small diameter. Then what I'm trying to do is to cover my set, my 0 Lebesgue measure set, by really effectively with some open cover. And I try to pick D so that this is still convergent. Okay. So again, as D goes to 0, this quantity here is increasing. And at some point, so if for D equal to 1, this is 0, as D goes to 0, it may happen that at some point these sums stop converging. And when these sums stop converging, this threshold is what I called the Hausdorff dimension. So basically the Hausdorff dimension will be the moment where these sums stop converging. Actually, they will go to infinity. And D is somehow measuring how small can I take this? How small can I consider this exponent? So this still converges. So this is the usual definition of Hausdorff dimension. So I hope I didn't bore you too much with this and I didn't lose you too much. But I will try to simplify this with something that is familiar for all of us. So I will consider the Cantor set. So I guess we all have seen this at least once. I have my usual Cantor set, I have the unit interval, and I start to remove the middle intervals. And then my Cantor set is just the intersection of all of these sets that I pictured, that I wrote here. And I would like to consider, okay, what is the Hausdorff dimension of this set, of my Cantor set? So if you allow me to ignore the endpoints of these intervals, I can consider these intervals that I draw here as open covers of my Cantor set. So the first cover has only one interval of length 1. The second cover has 2 intervals of length 1/3, and so on. So once I have these open covers, I am allowed to consider these nice quantities I had before, which I use in my definition of d-dimensional Hausdorff content. And then I just do the computation. So it turns out that in the first one, I just get 1. In the second one, I have 2 intervals of length 1/3d. In the second one, I have 4 intervals of length 1/3 to the d. And in general, what I get is I have an open cover that has 2 to the power n intervals, and each one has a length 1/3 to the power nd. And now I just can try to apply my definition. So these are my covers. So what does this tell me about the Hausdorff content? Well, it tells me that my Hausdorff content, my d-dimensional Hausdorff content, is smaller than this limit. And this limit, it's very simple. So basically, if I pick d big enough, this limit is 0. It's finite. If I pick d equal to log of 2 over log of 3, I get the threshold. I get 1. But if I take d smaller than this diverges. So what can I say here? Well, at least what I can say is that the Hausdorff dimension of my set is smaller or equal than this value. Now, if you want to show that the Hausdorff dimension is exactly this value, you will need to prove somehow that these open covers are basically optimal, or to use some other techniques. But this just gives you some intuition. If I want to estimate the Hausdorff dimension of a set, I just need some very effective way to cover my set. Okay, so this is really what we're going to use later. So in estimating the Hausdorff dimension of my invariant measures, I will define explicitly some nice covers on which I can do all the calculations and I can try to estimate the Hausdorff dimension. Okay, so I hope this gives some intuition. So now a few observations before I go to a little bit of the history of this and some previous results. So the Hausdorff dimension of a set is invariant by diffeomorphism. This you can check just from the definition that we had before. And for us, more importantly, this means that if I have a measure, I have a diffeomorphism, and I take the push forward of this measure, the Hausdorff dimensions are the same. So in particular, if I have a map, an irrational circle map, and I have some other map that is conjugated to it by a C1 transformation, then the Hausdorff dimension of these invariant measures are the same. Okay, so basically this, the dimension of the invariant measure depends only on the C1 conjugacy class. And we saw at the beginning that in general, you will expect your map to be at least topologically conjugated to a rotation. And since these maps are uniquely ergodic, you know who this invariant measure is. You know that this invariant measure is just the push forward of the Lebesgue measure by some homeomorphism. So if you want to understand, if you want to study the invariant measure of your circle homeomorphism, is somehow equivalent to understanding the regularity of this map, of this conjugacy. And then this somehow takes you naturally to consider the following question. So when does a topological conjugacy implies a regular one, which is called rigidity. And this is actually a very, very well studied thing, at least for circle diffeomorphisms. I will go through the main results in a second, but just a last comment, just a remark. Usually I'm working with maps that are conjugated to a rotation, but then what's the other scenario? When does my map is not conjugated to a rotation? The only possible scenario is that my map has what is called a wandering interval. So it's just a piece of arc of my circle whose iterates never intersect my initial arc. So in this case, I still have a unique invariant measure, but this time my measure is supported already in some Cantor set, which is basically the complement of these wandering intervals. So this is somehow a different setting because let's say that if you want to estimate the Hausdorff dimension of your set, you need to work with the wandering intervals, looking at the complement, try to control the size of these wandering intervals. But this is not what I want to do today. I will always assume that I'm conjugated to my rotation, so somehow my measure is supported everywhere in the circle, but still this measure is singular with respect to Lebesgue. And I will try to understand how small this full measure set can be. Okay, so now I will go through the classical results. So what can I say about the invariant measure for circle maps? And for this, I will need to recall some arithmetic conditions. So as I was telling you, the rotation number is some very important invariant. And arithmetic properties of this number will give me important dynamical information of my map. So the usual dichotomy when we consider rotation numbers is between Diophantine and Liouville numbers. So Diophantine usually is what we call badly approximated by rational numbers. So these are the numbers that verify an equality of this kind. Every time I try to approximate my number alpha by some rational number P over Q, if I want to get a very good approximation, this inequality is telling me that my denominator has to be very big in some sense. So of course, I can always get a limit of rational approximations to my irrational number, but this is telling me that if you want a good approximation, really the denominator has to be big. So big in some very quantitative sense, where so this exponent tau will play an important role in what we are going to do next. And this is the usual dichotomy that we have. So I have irrational numbers, I consider Diophantine, and the complement of the Diophantines are called Liouville numbers. So some important properties about this. So here, this is just some notations. So as I was telling you, I will try to consider Diophantine numbers according to the exponents that I have in this inequality. So when you put them all together, you let this constant gamma change, and you put all the Diophantine numbers with exponent tau in the same set. This is a full measure set. So actually, Diophantine numbers are of full Lebesgue measure. And if in the exceptional case where tau is equal to 0, this is what we call numbers of bounded type. In this case, this is not a full Lebesgue measure set, it's a set of Lebesgue measure 0. So this classification allows for some very nice results. So I will try to cover first the case of circle diffeomorphisms. So I will consider a map with a rational rotation number. And the classical result of Danjois says that if your map is sufficiently regular, so for example, if your map is of class C2, then the circle map is conjugated to a rotation. So what I was saying before, I don't have wandering intervals. And moreover, we have a result. So this is really a very, very summarized version of many, many important results that spanned over 3 decades. So I am surely forgetting many names here. So I just put some of the authors that made contributions on this. So my summarized version is the following. If you take a circle map, a sufficiently regular one, and you suppose that its rotation number has some nice arithmetic properties, so for example, it's Diophantine, then it turns out that your map is not only topologically conjugated to a rotation, but it's actually smoothly conjugated to a rotation. So why this is important for me? Well, this means that my invariant measure is actually a very regular one. I can express it as density times the Lebesgue measure on the circle. And here I have no need to consider, for example, the half-door dimension. My measure is actually not singular with respect to Lebesgue, it's just basically a multiple of Lebesgue measure. So I have a very, very good behavior. But again, here we need to assume something on the rotation number. But the moment that we get out of this setting, if I consider rotation numbers that are not Diophantine, I can get a very different behavior. So there's an example by Arnold that shows that regularity alone is not enough to say anything about the invariant measure. So basically, he constructed an example of an analytic diffeomorphism with irrational rotation number, which will be of Liouville type, such that the unique invariant measure is singular with respect to the Lebesgue measure. So I do need to assume something of the rotation number if I want to say something of the invariant measure. But actually, if you are willing to decrease the regularity a little bit, the behavior can get as distorted as you wish. So there's a result by Victoria Sadovskaya, which shows that for any Liouville rotation number that you pick, there are examples of circle diffeomorphisms with that precise rotation number, whose invariant measure is not only singular, but has any half-door dimension that you choose between 0 and 1. So you can have a behavior as distorted as you wish. Again, this when you assume that the rotation number is Liouville. So the circle diffeomorphism the circle diffeomorphism case is very well understood. So that's one of the reasons why I'm considering already critical circle maps. So let me move a little bit forward and consider the case of critical circle maps. So for critical circle maps, we have an analogous of Danjois results, which says that if you add a little bit of regularity, in this case, I don't need C2, but C3, then my map is actually topologically conjugated to a rotation. This means I don't have wandering intervals, my measure is supported in the whole circle. But notice that this time, I cannot try to say, okay, but what is the regularity of the conjugacy with the rotation? Because in this case, I don't expect the conjugacy to be C1. Why? Because in one side I have critical points, in the other side I don't. So I cannot expect to be C1 conjugated. So So I cannot expect to understand the regularity that easily as we did before in the circle diffeomorphism case. In this case, this rigidity property takes a different flavor. Here, what you can ask is if you have two critical circle maps that are C0 conjugated, so for example, they have the same rotation number, when are they C1 conjugated? And actually, this is a very important conjecture. So it has been conjectured that if you have two critical circle maps with irrational rotation number and the same signature, so I will define what the signature is in a moment, but basically something that encodes the number of critical points and their criticalities, then if these two maps have this same signature, we expect them to be C1 conjugated. So what is the signature formally? If I have a critical circle map with n critical points, the signature is just the number of critical points, the rotation number, the criticality of these critical points, and some values that tell me basically they're somehow encoding the distance between these critical points according to the invariant measure. Okay. So why is this? Because if I expect two critical maps to be conjugated to each other, I expect them to have the same number of critical points. I expect the conjugacy to send critical points to critical points. And since they are uniquely ergodic, I do need for their distance to be preserved. So basically, the distance between two critical points in one map and in the other are the same according to the invariant measures. So the conjecture is that if these signatures are the same, then my maps are C1 conjugated. And in particular for me, since I'm interested in the dimensional properties of the invariant measures, if I have two maps that have the same signature, this will imply that the Hausdorff dimension of the invariant measures is the same. So let me just comment that this conjecture is still open in full generality, but great progress has been made in the case of exactly one critical point, and assuming that this critical point has odd criticality. So basically, I only have one critical point, and my point behaves as x to the 2n plus 1 for some n. And this is really a work spanning several decades and due to several authors. And it's exactly here where you can see a little bit of the quasi-conformal techniques appearing. So it turns out that here we have this big restriction on odd criticality. And this is because actually to understand the renormalizations of these maps, the techniques that are available to us is some complex extensions. So we'll need some extensions of our maps, and we will need some quasi-conformal techniques and quasi-conformal dynamics to prove what is called exponential convergence of the normalizations. And this is why the results that we have for the moment are only available for odd criticality, because if I don't assume that my critical point behaves as x to the 3, for example, x to the 2n plus 1, I don't have access to these extensions, and then my theory somehow breaks. So this conjecture I mentioned before, it's open for several critical points, for one critical point of criticality different than an odd number. And again, this is one of the points where the quasi-conformal techniques appear, but sadly, this is not what I'm going to speak about today. So I just wanted to mention. And this is just what I said before. The importance of this conjecture for me in this talk is that if this is to be true, then the dimension of the Hausdorff dimension depends only on the signature of my map. So this is why I said at the beginning, it's not so weird to expect that I can somehow relate the Hausdorff dimension to the rotation number, because this is somehow what you expect. Okay, so now after this big introduction, I'm able to tell you what we know about the invariant measures of critical circle maps. So as I said at the beginning, what we know already is that the invariant measures are singular with respect to Lebesgue. But we know a little bit more in some particular cases. Actually, if I assume that the rotation number is of bounded type, so again, this was my zero measure set in the Diophantine conditions, then we can show that the Hausdorff dimension is smaller than 1 and bigger than 0, but we don't have an explicit estimate. And again, this only covers a set of rotation numbers of measure 0. So just to recall, the bounded type was what I defined as the exponent tau being 0 in the definition of Diophantine. But actually, bounded type admits a very nice description using the continued fraction. So basically, a number is of bounded type, an irrational number is of bounded type if its continued fraction has only, if the terms in the continued fraction are uniformly bounded. So these are basically the only cases that we know. And this takes me finally to the statement of the theorem that I wanted to talk to you about today. Is what can we say in bigger generality? So take an irrational critical circle map. Then I want to study the Hausdorff dimension of its unique invariant measure. And I can say the following. I can say that if my rotation number is Diophantine for some exponent tau bigger or equal than 0, then I can bound from below its invariant measure using this Diophantine exponent. And on the other hand, if I assume that my rotation number is not Diophantine, then I can bound from above its Hausdorff dimension. Okay, so this is the result I wanted to talk to you about today. And it's the explicit bound between the Hausdorff dimension of the invariant measure and the rotation number. More particularly with the exponent of the Diophantine condition that I assume, or that I suppose is not, so the condition I assume or is not verified, and I obtain explicit bounds. Okay, so are there any questions so far? Okay, so just one comment before I go a little bit more into explaining a little bit the techniques on the proof is, as you might have noticed, I'm always assuming this C3. And you may wonder, okay, why C3 when in the circle case we just had, in the diffeomorphism case, we had only C2 or C1 plus something. Well, it turns out that we usually work with C3 because many things depend on estimates that we obtain using the Schwarzian derivative. So the point is that when you assume that you have critical points, then your derivative, of course, gets to be 0, which means that you get unbounded distortion. So when you have unbounded distortion, one way to try to control things is through using some cross ratios. And it turns out that the distortion of cross ratios of this kind are very closely related to the Schwarzian derivative. So if you assume that the Schwarzian derivative is equal to 0, for example, for a map, then the distortion of these cross ratios, actually they are not distorted. If you assume that the Schwarzian derivative is positive or negative, it means that these cross ratios are always increased or decreased. So again, since I have unbounded distortion in the sense of one-dimensional dynamics, one way to work around is to consider cross ratios. And these are very closely related to Schwarzian derivative. And many of the things we can do is thanks to this Schwarzian derivative. So that's why in many cases we consider our maps to be C3. So now I will try to tell you a little bit about the proof. And now the proof will make use, of course, of some very classical facts on circle maps. So I will start by introducing what is called the first returns. So given an irrational number, we define the return map, the return times, as follows. So maybe let me try to make a small picture. I have a circle and I have a point, and I will consider this rotation R alpha. And then what I'm trying to do is to consider, okay, I have my point X, I have its first iterate, and I try to find the next iterate that gets closer than this distance. So I will iterate a little bit more, and at some point I get closer. So this will be my first return time. This will be my second return time. And I repeat this process. So I continue iterating until at some point I get over here and I get closer than before, and this will be my third return time. So I'm just trying to encode in a way the sequence of ordered closest returns of X according to this map R alpha. Okay. And just something that one has to show, but it's very well known, is that these closed returns appear one to the left and one to the right of my point. So if my first return was here, my second one appears on this side, the third one appears on this side, and so on. Okay, so these first returns play a very important role in theory. And just to exemplify what can you do with this kind of thing, so just a small application of first returns is the following. Suppose you have an irrational circle map, a diffeomorphism. This time is not the rotation, and its rotation number is equal to alpha. Then I will use these return times that I defined before that are associated to alpha to define these quantities. So basically I have a point X, I have this very big iterate that takes me very close to X, and I consider just the minimum over all circle, the maximum over all circle. And then just with this, if you have some control on these values, on this small m and this big M, you can show things of this kind. If the ratio between these two values it's bounded up from above and below, then your map is C1 conjugated to a circle rotation. So actually, just from this assumption, so maybe let me use this. Just from this assumption here, you can give a 10-line proof of the fact that F has to be C1 conjugated to a rotation. So these are very strong properties, and these first returns are very, very important and very closely related to renormalization. So we'll say a little bit more about them in a second, but I just wanted to say that these quantities are very, very important. And the way that we take them from rotations to circle diffeomorphisms is through the rotation number, because I know that in general, my map is conjugated to the circle rotation. So I just can take everything I have for the circle rotation, I can take it to my diffeomorphism through the conjugacy.
So I have a quick question. I mean,
yes,
if your map is just the rotation by alpha, I guess that these return times are related to the continued fraction expansion?
Yes, we will see that in a second. It's a very good remark, and we'll see that in a second. Thank you for the question. So using these first returns and these return times, we can define what is called dynamical partitions. So if you take a circle map with irrational rotation number and you have the return times, you can fix a point and you can consider these intervals. So basically this is a bit what I was trying to draw before. I have the circle, I have my point x0, and I have the first return times. So let me say that this is qn. Over here I have xqn plus 1. And this interval in is just telling me that sometimes I pick this small piece of arc, or sometimes I pick this small piece of arc. It depends on whether n is even or odd, because as I was telling you before, sometimes my first returns appear to the left or to the right of my point. Or okay, since I'm in the circle, I should say clockwise or counterclockwise direction. And using these arcs, which are my closest returns, I can consider iterates of these intervals to define what is called as dynamical partition. So I take these arcs, in minus 1, in, which were the ones that I was drawing here before, xq n and xq n. Let's So xqn minus 1 and xqn. So taking just iterates of these two intervals here, which are my first returns, I can define a partition of my circle. And I will use this partition to study my invariant measure. Why? Because since I'm considering iterates of the same interval, all of these intervals will have the same measure according to the invariant measure, but it might happen that they don't have the same Lebesgue measure. And this is what I will exploit in trying to understand the Hausdorff dimension of my invariant measure. Okay. So just a small remark, this is very closely related to renormalization. So in normalization, what we do is consider a first return map. So usually these intervals are used to define this interval in which I'm inducing my map to define the renormalization. And again, this is very closely related to this rigidity theory I mentioned before. We are not going to need this, but I just wanted to mention it here. And as Mario was saying before, these returns are closely related to the continued fraction. And you can really see this in the way that these dynamical partitions refine each other. So if I consider two consecutive dynamical partitions, you can see here that in the nth dynamical partition, I have iterates of this interval, in minus 1. Oh, sorry. Iterates of this interval, but these iterates of this interval do not appear in the next step. In the next step, I only have iterates of this interval, which was here before, and iterates of this interval. So what is happening is that these intervals, these in minus 1 intervals, all over here, they get chopped off, they get chopped into smaller pieces. So how do they get chopped? So you can see this using the continued fraction. So what happens is the following. So this big whole thing is my interval in minus 1. And what happens is that this interval here, in, will enter here several times. All of these are iterates of my map in. And how many iterates do you get? Well, these are very closely related to the continued fraction. So you will get an iterates here. So this is the way how they refine. And then you have this very nice property here. So what you get is something of this kind, this nice formula here. So let's say this in minus 1 minus this very small piece here gets chopped up into many pieces, which are all iterates of the same interval in. So this formula is what will be essential for me, because this is everything that we're going to use now. The point is that in the rotation case, of course, I'm drawing them here as all having the same length. What will happen is the following, is that these iterates will have the same invariant measure, but they don't necessarily have the same Lebesgue measure. So this is usually not true. So if I can somehow say that some of the iterates get very, very small, very contracted in the Lebesgue measure sense, I will be able to build full measure sets according to the invariant measure that have very small Lebesgue measure, which again was what I needed to get to estimate my Hausdorff dimension. Okay, so I will just draw a picture of what happens in the critical circle case to say that this is what will happen. Will look very different from what it had before. So this is precisely what we had before. This is our big interval in, and this time all of these are iterates of the same intervals. But then you see that they're getting smaller and smaller. And what happens is that the more iterates I have, the smaller they get, and all of them get cramped up here in the middle. And then the bigger my continued fraction gets, the smaller these intervals will get. And using this, I will be able to estimate my Hausdorff dimension. So this picture is what will happen if I only have one critical point, and this particular dynamical partition is associated to this point. But in general, I will have some more critical points, and my partition will look like this. I will have big intervals wherever a critical point is found, but in the middle of two intervals close to a critical point, all my intervals get very small. And this is exactly what we're going to use. Okay, so I think I might need to go a bit faster. So just to justify why we have this kind of behavior that I was saying before, that the intervals in the middle get smaller, this is due to the Schwarzschild derivative. We can show that high iterates of my map will get negative Schwarzschild derivative. And there is a very nice property for maps with negative Schwarzschild derivative. So this is a lemma due to Yokos, which says the following: if I take a map F, which is defined in a union of intervals, of adjacent intervals, such that my map F maps the one interval to the next. So just let me go back for a second and exemplify this here. So this is exactly the behavior that we have for the map FQN. The map FQN is mapping this interval here to the next, to the next, to the next. And what we can show at the end is that this has negative Schwarzschild derivative. And if I have a critical circle map, so I just go back to this lemma, is just to say that I will apply this general result to estimate the size of the intervals in the middle. So what this lemma is telling me that if I have my interval, which is expressed as a union of intervals, so I have something like this, and each one is mapped to the next, then the intervals in the middle, the more intervals I have, the smaller they get. The smaller they get compared to the bigger one. So actually my picture doesn't look like this. My picture has to look as we had before. The intervals on the sides will be big, and in the middle, the intervals start to get very small. So just a picture of what really happens in the circle case is the following. Here, if you consider this interval here, so maybe with this, if you consider this interval here, and you consider iterates by this map, FQN plus 1, then the next iterate is here, then here, then here, then here, and they get very, very small. And the more iterates I can make, the smaller they get. All of this because I can get some bounds on the Schwarzschild derivative, and I can do many things in the case of critical circle maps. Again, all of these things is not me who proved them. These are very well-known facts, which are due to Arman, Schwantek, Hanin, which tell you that if you have a critical circle map, then what I was saying before, high iterates of this map has negative Schwarzschild derivative. This is due to the fact that I have a critical point, which has, my derivative gets close to 0. This leads to the fact that high iterates get negative Schwarzschild derivative. And I also get some nice property that I need in my assumptions for the Yokos lemma, which are that adjacent intervals in the dynamical partitions have comparable lengths. So again, all of these are very well-known facts for critical circle maps, and it's very different from what you get in the case of circle diffeomorphisms. So for example, in the case of circle diffeomorphisms, you can get two adjacent intervals in the dynamical partitions whose ratio is arbitrarily big or arbitrarily small. This never happens in critical circle maps. So it's a very, very different behavior. And as you can see here also, things are always holding for any irrational rotation number. In circle diffeomorphisms, we always have something for Diophantine, something different for Liouville, but in this case, things hold for any irrational rotation number. So somehow you have some more robustness of phenomena, some more rigidity. So think my time is almost up, but then I just wanted to mention what we do with this very quickly, if you give me just 2 minutes. So again, all I'm going to do is to play with this nice formula. And again, the important thing for me is that intervals here have the same measure according to the invariant measure, but have different Lebesgue measure. So using all the things that I stated before, you can really estimate the Lebesgue measure of these intervals to conclude what I said before. The middle ones really get smaller and get smaller in a quadratic sense. And then this is enough to do the proof. So how does the proof go? Well, first, you restate the Diophantine properties using continued fraction. So it turns out that Diophantine properties are also very closely related to continued fraction, and basically tells you that you are Diophantine if you get some control on the possible growth of your continued fraction. So basically, you are Diophantine if you get some control. If you don't get some control of this kind, you are Liouville. And then, once I have my critical circle map, I have its rotation number, I have its unique invariant measure. If I suppose that my number is not Diophantine, this means that I have a very big growth of my continued fraction, which means that I get intervals in this dynamical partition that get very, very, very small. So using this fact, I can just build my full measure sets using the middle intervals as in the picture. And then you get some upper bound for the half-dot dimension in the same way that we get the upper bound for the example of the Cantor set. On the other hand, as I was mentioning before, if you want a lower bound, you can use some other techniques. So the point is that this actually will follow easily because we have a lower bound for the elements of the dynamical partition that follows from these lemmas that I mentioned before. And we have results of this kind. So this is called the Frostman lemma, which tells you that if you can somehow estimate the invariant measure for small intervals and compare them to the usual size of an interval, then you get bounds on the half-dot dimension. So since I have a lower bound for the size of these intervals, and I can also have a bound for so using some properties of the dynamical partitions, I can get a bound for the measure according to the invariant measure. I just compare these two and I get a lower bound directly. So, and basically that's it. That's how you get some lower bounds using dynamical partitions related to the rotation numbers. So sorry, I think I went a little bit overboard on time, but thank you.
Yeah, thanks a lot. Let's thank the speaker. And let me open the discussion, comments or questions.
I guess, can I ask a question here? Am I audible?
Yes, please.
So you had this proposition with a big M and a little m, and
Yes.
the characterize that implied C1.
Yes.
First, there must be some kind of converse to that. And secondly, maybe can you also do something with second differences to tell when something is C2?
So you're saying about this proposition?
Proposition with big M and little mn and little mn, big mn and little mn.
Yes, I think it was first returns was somewhere here. Yes, here.
Yes, yeah.
Yeah.
That looks like you could do something more general, but also does it have a converse?
Yes, yes.
Kind of converse.
Yes, I mean, if you are, I mean, the converse, if you are C1 conjugated, yeah, for sure these two are bounded. Yeah.
Mm-hmm.
This is.
And how about if you could you do something to get describe C2 and C3 using
Yes, no, of course. So that's exactly what I mean.
Differences.
Yes, no, I mean, this is exactly what happens. I mean, this is also another proposition of something that I proved. This is like, classical thing. Usually what happens is that you get a C1 conjugacy, and then people try to bootstrap somehow the regularity in order to get something better. Yeah. But yeah, this is how the proofs of a smooth conjugacy go. But yeah.
Could you even get Lipschitz classes?
Yes, exactly. Usually you go from Lipschitz to C1, and then you go over. Yes.
Well,
But
okay, fractional ellipses classes, lip 3/5, and
yes, I mean, I am not sure right now. I mean, on the spot, I will not be able to tell you what are the exact
okay.
things that you
Thank
can
you
get.
very much. I like to talk a lot.
No, thank you for staying until the end.
Yeah, are there other comments or questions?
Yeah, I wanted to ask, so we basically kindly asked you to talk about this paper because we're all interested in hearing about it, but I think it's about 2-3 years old. Is that correct?
Yes.
Is there any like related questions or follow-up questions that you're currently still thinking about, or is it something that you have let rest since then?
So the thing is that what I did was to change the class of transformations, and then I tried to consider not critical circle maps, but circle maps with breaks, which means that I have a piecewise smooth circle map. So instead of having a critical point, I have a point where the derivative has a break. So an example of this is just piecewise linear map.
Okay.
And then you can try to ask the same question. You can say, okay, I know that I am C0 conjugated to a rotation. What is the half-order dimension of the invariant measure?
Mm-hmm.
And so this required some different techniques, some interval exchange transformations, renormalization theory, let's say. But at the end, what I recently proved is that in this case, you have 0 half-order dimension.
Okay.
In this other setting, you can show that the half-order dimension of this unique invariant measure is 0. But then this used some different techniques. So it required using some interval exchange transformation theory. Yeah.
Okay, thanks for sharing.
Other comments or questions? Well, I have a question. Can you go to your main theorem again?
Yeah, sure.
Mhm.
So is there any hope for getting bounds in the other direction in these cases? Or is this just a silly question to ask?
No. Yes, I mean, there should be, and for example, here, this, for example, this upper bound applies only when I assume that my number is Liouville, for example. But we already know that if your number is of bounded type, so very, very non-Liouville, you have an upper bound. This upper bound, so you don't have an upper bound explicit, but you know that the half-order dimension is smaller than 1. So this is mostly a restriction of the technique. So the way I did it, I really need explicit geometric construction. And then because of this, I get these restrictions and I get a relation with the Diophantine exponent. But one could expect that you get some other bounds using different techniques. Yes, because for example, again, in the case of bounded type, you know that this is more than 1, but even in the bounded type case, we don't have a explicit bound. I cannot tell you if my bound is M, then my half-order dimension is bounded by something. This we don't know. But yes, I mean, I think that it should be possible, but I don't know how to do it.
Yeah, thanks.
Thank you.
Comments or questions?
I guess one more. How much, if the number of critical points gets very, very big, what happens to nu? How does,
So
when you get a lot of them, it would sound like things were really shuffled. So
yeah, so what you will expect to know is that it will grow a lot. That is exactly what you expect, that this nu is growing. But it's not so easy to get a track on this constant. But yes, what you expect is that it gets very big. So somehow the bound gets lost a little bit.
okay.
Yeah,
Thanks.
expect it to grow.